Hi, morning people, can you guys hear me? Alright, well, whoever isn't here, they'll just see the recording afterwards regardless. So, today we're basically going to be doing problem set 3. And in particular, we'll be doing from questions 1 to 5. I believe I might be able to do question 6. Let's see. Yes, I can do question 6 as well. But question 6 will be like a really short abbreviated version. Alright, so let's start with question 1. So question 1 here is asking for the canonical form of this h of z transfer function entirely. And the thing that we have to pay attention to when we're drawing the canonical form is that we try to pay attention to it from lecture 14, where we had the canonical form here represented by this form here visually. But what we wanted to pay attention to is that the equation for h of z needed to be set up in a particular order, such that the first term here, on the numerator, being the b naught term, is what you need to pay attention to make sure that will be the first term here on your right hand side. And the first term in the denominator here needs to be 1. So once you have the equation set up in this general form here, you can draw a canonical form for any h of z equation accordingly, and just by mapping it using this general form here that you're seeing visually. So going back to what we have here is the canonical form here is that we have it as h of z. So we have our b naught here being 5, and the first term in the denominator here is 1. So we could just use the general standard form that we just now saw in lecture 14 to actually draw this. So as of such, when we're drawing this, so I have to use Visio for this. So we'll put our, let's see, where's my text box? Right. So we're going to put our x of z here, and then we'll put y of z here accordingly. Then we're going to be putting our summation point there. Drop a connector from here to here. Right, so this will be plus. Copy that as well. Right, see how that looks here. Okay, everyone's seeing that. Alright, so backtrack a little bit to our equation. The first term here was 5, so this is going to be the first term on the right hand side being our b naught term. So we could drop a square here. And inside here, we can say this is going to be 5. Move this one side. Copy that because we need to put an exclamation point leading to y of z. Then we could put our connectors here accordingly. Oops. Right. And the summation point here is also going to be summation addition. Right. The next thing that we're going to have to put in here would be the first delay level. So if you watch back here for canonical form, each one of these levels that we observe here, the first level here would be the first delay, whichever one was z(-1). The second level here would be when we compound these z(-1s together, so you get z(-2). So at this vertical level here will be the z(-2) level, and so forth here. This will be the z(-3) level, and so forth. So because we only have up to the first order here for h of z, only z(-1), that means we only need to have one level of z(-1) when we're drawing this. And on the right hand side, because we already accommodated for this 5 here, and now we're trying to accommodate for this 2 z(-1), that means that we're going to have to put a 2 on the right hand side underneath the z(-1). So the first thing we'll do is copy this, and this is going to be z to the power -1. You drop in a connector here, and then we'll put in our block here, and this is going to be 2. This would go here, and this would go here. The last thing we haven't accommodated for would be this -0.8 here, z(-1) on the denominator, but this is going to be our A0 term or A1 term, as we saw in our lecture. So this will be the A1 term here accordingly. And that A1 will be such that we need to accommodate for it in our diagram right here. But notice that this is going to be -A1 accordingly. So on the right hand side here, these are positives. So B0, B1, B2, and so forth were positive. But the left hand side, this is going to be -A1, -A2, -A3, and so forth as they keep on going. So in going back to our problem set here, we basically saw that it was a -0.8. But we take the negative of this is going to be positive 0.8. So when we drop our block here to indicate our feedback, instead of this being -0.8, we're going to have to say that's the minus of that, so this is going to be 0.8. Then we could draw a connector here. Move this a little bit this way. Hold on. Move you one side, move you one side. Put you there. And we draw a connector here. And that is the end for question 1. So anyone has any questions as to how we actually went about doing question 1 in particular? So the sign for the feedback here, where you're watching, remember when you're watching it on the lecture, this needs to be minus A1. So here, when you're watching it on the denominator, you might say, okay, this is positive A1 and so forth, right? But that's, yeah, you might say, okay, that's positive A1 here, but whatever the value of A1 is here, you need to put that as the negative value here when you put it in the diagram. The sign for the feedback going in here is still positive, yes. So these summation points here are always positive feedbacks. They're not negative feedbacks, they're always positive. Whether it be on the left hand side or on the right hand side. So no matter what summation point you're using for anything regarding the canonical form, all the summation points here will be positive feedbacks all the time. It's just the signs for the left hand blocks will be negative or whatever on the denominator, and for the right hand blocks it will just keep positives. Alright, so that's question 1. Question 2 is to examine the figure question 2, and we need to figure out what is each of z. So this will be the figure here for question 2. And I'm going to have to annotate this a little bit. What we're going to have to do here in annotating this is that we're going to have to figure out, we need to use some intermediary signals at the output of each one of these summation points to formulate our entire transfer function. So let's see how I'm doing this. Alright. So for the output here, this is not how I'm thinking about, so so you have to excuse my crappy handwriting at this point. This output here we're going to put as W1. The output here would be W2. The output here would be W3. The output here would be W4. And yeah, I think that covers all our summation points regarding for this. The shape doesn't matter if it's a box or a triangle. The reason why triangles are used here is because you just wanted to indicate the direction of which it's going. But once you put the arrowhead, we already know which direction it's going. Alright, so because we set up W1, 2, 3, and 4 here currently to be our intermediary signals, that means now we can start formulating for the outputs here currently as well. So let me split this. Need a Word document. Alright, so max this file a little bit. Alright, so for W1 here, we can basically formulate this in terms of the output and the input. Oh, whoops, I need to put in one more thing. Right, so let's call the output here y of z. And let's call the input here x of z. So we could basically say here, for this first output here where we have W of 1, let's formulate an equation to map it in terms of Y for what the output is here, to get it in terms of W1, and then we can replace this accordingly to get it in terms of X of Z. So our first equation that we want to put here is that Y of Z is going to be equal to 5 of W1. Because we only care about what is the output here going towards regards for this feed forward part here. So we only care about this feed forward part here accordingly. And we're watching it in terms of W1 here. So Y of Z here needs to be equal to W of 1 accordingly. Now, because we're watching it in terms of W of 1, that means we need to figure out what W of 1 is going to be. And W of 1 here if you watch this accordingly to this summation point only, is that it's going to be 3xz plus W of 2. So there's 3x of z plus W of 2. And we can substitute W of 1 here into Y of Z. So Y of Z will now be equal to 5 into this here, which was W of 1. And then we get 15x of Z plus 5 W2. Now, we can also continue this accordingly, because now we can actually figure out, okay, what is W of 2 going to be, regards to this. And W of 2 here, we need to incorporate this Y of Z here that is going downwards, multiply by Z to the negative 1, and then multiply by this 26 here accordingly as well. So, in writing our equation for W of 2, W of 2 is equal to, let's take the positive first, so the positive part here is going to be positive W3 minus 26, because we have this 26 coming in here, and this part here in the summation point is negative, and this 26 needs to multiply by z to the negative 1, and that z to the negative 1 is coming from our output here, which is Y of Z. So it's going to be 26 z to the minus 1 of Y of Z. So that means we could formulate Y of Z here from before equal to 15 x of z plus 5 into what our W2 here was accordingly. And then we do the same thing again for W of 3. So W of 3 here was going to be the output for this summation series here. We need to make sure what are going to be the inputs. So we have a W of 4 input here that is coming in. And then we have the next input here, which is going to be 10 multiplied by z to the negative 1, and this is also coming from the input, so this will be x of z. So our w of 3 equation is going to be equal to w of 4 plus 10 z to the negative 1 of x of z. And then we substitute this into the y of z equation. It will be 15x of z plus okay, so let me expand this out a little bit. This is going to be y of z is equal to 15x of z plus 5 w of 3 minus 130 z to the negative 1 y of z. Alright, so then we can say here this basically is going to be plus 5 into our substitution for w of 3 here, which is going to be w of 4 plus 10 z to the negative 1 x of z minus 130 z to the negative 1 of y of z. Oh, let me don't save that. Subscripts underscore doesn't do subscript for me in this particular version I would. I think it's basically a personal setting I might have to modify at some point. But thanks for the suggestion though. I'll figure out how to set it up. Right, and then we can expand this out a little bit more. So y of z is equal to 15x of z plus 5w4. Yep, see, doesn't work. Plus 50 z to the negative 1 that minus 130 that. And then the last thing we'll have to do here is for the W4 output. Now the W4 output will be, we have a positive input coming in here, and then a negative input coming in here. And that will be the summation of the two will give us W of 4. So we want to watch this accordingly for the positive input first, because there's going to be 3 multiplied by z to the negative 1 multiplied by z to the negative 1 here accordingly again, and this is going to be multiplied by x of z. Alright, so this is going to be w of 4 is equal to 3 multiplied by 2z to the negative 1, so it's going to be z to the negative 2 x of z, and then we have to accommodate for this part here, which is going to be on negative feedback. So it'll be, this is minus 5 multiplied by z to the negative 1 multiplied by z to the negative 1, and this is going to be y of z. So it's going to be minus 5 z to the minus 2 of y of z. So then we can substitute this in to our y of z equation, 15x of z plus 5 into our w4 here accordingly. And then we have the remainders here. And then we can expand this out. 15x of z plus 15 z to negative 2. Oops. Minus 25 z to negative 2 of that. Plus the remainder part here. Right. Yeah, the last equation is basically what you're doing throughout the entire thing is that you're just calculating for the outputs of each one of these summation series. So you'll be calculating for W1 here, then W2 here, then W3, and W4. And because you start with W1 here mapping in terms of Y and X, it makes everything map back in terms of Y and X when you do the substitutions. So now we have everything in terms of Y and X here, was just to make sure that we could formulate this in terms of our transfer function. So I want to simplify this out a bit. So y of z here is equal to 15x of z plus 5 into 3. Now I expand that out, plus that. Okay. So I'm going to say y of z here. I want to carry over all the y of z's onto the left hand side. So we have x of z, y of z here. Right, so y of z plus 25. Okay, y of z plus 25 that's negative to y of z plus 130 y of z is equal to 15x of z plus the 15 z to negative 2x of z plus this here. Then the next step I want to do is that I want to factorize, so I want to pull out the y of z's. So it's going to be 1 plus 130, let's see, z to the negative 1, plus 25 z to the negative 2 right is equal to x of z, and then we pull this out accordingly. So x of z here is going to be 15 plus whoops, right, so I made one mistake. No, I didn't make a mistake, okay, no, I'm fine. Plus 50 z to the negative 1 plus 15 z to the minus 2. Alright, so let me just double check back my arithmetic here for a little bit. -25 to negative 2 that's minus 113 that's. Alright, okay. Yeah. So I'm okay. So it should be 15 that's 15 to negative 2 minus 25 that plus 50 to negative 1 minus 30 that's right. This would be 1 plus 130 plus 25. Okay, right, good. So now that we have it in terms here of y and x, we could just basically get this in terms of y divided by x. So the last thing we want to do here is to organize this into a transfer function, which is going to be y of z divided by x of z, and the y of z will be on the numerator. No, sorry. The x of z terms here will be on the numerator because we're cross multiplying in this case. So this will going to be in terms of fractions. So this part here would be on the numerator, and this part here would be on the denominator. And that is actually how we obtain our transfer function here accordingly. Alright, so any questions regarding how we went about this entire process to get our transfer function? Just save this one time. Okay, we're pretty much okay then. Alright, so that actually is the end of question 2. So question 3 here is to draw the canonical form of the figure question 2. In order to do this, we need to make sure that we finished out question 2 here accordingly to get it into that form. So let's split back here. So we're going to be watching this accordingly to this equation that we obtain for question 2. The output of question 2 here was that we got our transfer function here in terms of y of z and x of z, and then we organize it into the standard form here. And if you can recall from lecture 14, the standard form for a canonical representation needs to be that the first term on the denominator needs to be 1, and then the entire numerator and denominator need to be organized in terms of z to the negative 1 in descending powers of z. So once we have it in that standard form here, we can just replicate the general form that we observe here for any canonical form equation that we wish to represent visually. So because our equation here goes up to z to the negative 2, that means we're going to have 2 levels accordingly for each one of the z. So we'll have, if we're drawing this diagram, we only have up to this part here to draw. The b0, b1 and b2 will be the coefficients of the numerator accordingly. So this will be for the z to the 0, this will be for the z to the negative 1 and z to the negative 2. And the negative a1 and negative a2 coefficients will be for where we have the z to the minus 1 and the z to the minus 2 coefficients in the denominator. So actually let's draw this and see what it looks like. So I'm going to copy this here to make my life a little bit easier. I'm going to expand out onto it. Move you up a little bit. Right. So let's backtrack a little bit to watch our denominator and our numerator. So going back here, we know that basically the b terms are going to be on the right hand side of this, so we're going to be watching the numerator. So this will be 15, 50 and 50. So this term, first term here is going to be 15, the second term here will be 50, and now because we need to incorporate a next level of z to the negative 1, we'll be putting that there, and this last term here is going to be 15. We could draw in our connectors. that should satisfy how our actual thing looks. If we wish, we could put in summation points. That's not an issue. But the summation points basically will be that this is just replicated accordingly for this part here and this part here as well. So I'm just going to replicate one of these summation points. Put you there. Copy you. Put you there. Nice. And then for our denominator, we know that we had the 1 here. This needs to be 130 and the next one needs to be 25. But because these are positive here, so it's to be a positive 130 and positive 25, but they're going to be negative A1s from the lecture. So even though A1 here was positive, as we can see here from the lecture, A1 here on the diagram needs to be negative. Same thing for A2 as well, it needs to be negative. So we have positive 130 here for A1, but this here is going to be negative 130. And similarly, because I need to drop in another summation point here, alright, so we connect that here, connect that going up here. Move that there. Let's see, okay, I have my plus sign. Alright. Copy you. Right. The next block we have to put in is this 25 here, but this is positive 25, and because it's on the left hand side, it's going to be negative 25. So this here will be minus 25. We could draw in our connectors. Make this look a little bit neater. And put in our summation point here. Right. And that basically is how we actually represent our question 2 canonical form visually for question 3. So basically what we just did here is that once we had the equation here for y of z in the standard form required for canonical form, we then pay attention to how the diagram is drawn in lecture 14 here on slide 25, and once it's set up accordingly in that standard form, we just draw it back and we replicate where B0, B1 and B2 need to go, and A1 and A2 needs to go as well. The thing we need to pay attention to is that A1 and A2 here will have negative coefficients when we're going about doing this. So if A1 here is positive on the denominator, when you put it in the diagram it needs to be negative accordingly, and so forth. So that is the end of question 3. Any questions regarding this at this point? Alright, it seems like it has no questions, so I'll move on to question 4 in the meantime. So, question 4 here asks what are the conditions for distortionless transmission? And question 4 basically can be extracted back out from the lecture notes itself. In particular, this will go down to when we're talking about lossy and lossless transmission. So those lecture notes should be somewhere going down towards the end of all the lectures. In particular, I know I recap it in the last lecture, which is lecture 23. So you just want the conditions for distortionless transmission by watching those lecture notes. Question 5 here is to design an n-term moving average filter where the first null point is at 100 Hz and we're going to be using a sampling frequency of 500 Hz. So I'm going to split this accordingly again. I'm going to go back here. So this solution here was for, put this in question 2 solution. And let's break into a new page. This is going to be question 5 solution. Alright. So we're watching question 5 here currently for an n-term moving average filter where the first null point is at 100 Hz and the sampling frequency here is going to be at 500 Hz. So we know from our notes that the zero crossing, which is capital omega, if I could find it, is equal to 2 pi divided by n. But we also know that capital omega here is equal to common omega multiplied by t, which can map to the same thing here, which is 2 pi on n. So then we can rearrange this entire thing here to get in terms of common omega, where on the denominator here this is going to be nt. We also know that n here is equal to our sampling frequency divided by f, which is going to be our null point frequency. So this here is going to be 500 Hz, which is our sampling frequency, divided by our null point frequency, which is 100, is equal to 5. That will be the number of terms that are required for n-term moving average filter. So n here is going to be equal to 5. Because this is a moving average filter, we basically can represent this using our standard moving average filter equation, which is going to be y of n is equal to 1 divided by n into x of n plus x of n minus 1 plus dot 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 x of n minus brackets n minus 1. So in this case, y of n here will be equal to 1 divided by 5, which is going to be 0.2, into x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3 plus x of n minus 4. Now, the reason why we say n here is 5 terms and we only go from n to n minus 4, if you count the number of terms here, this is 1, 2, 3, 4, 5 terms accordingly. So we will satisfy n here being 5 terms in the moving average filter equation, and the 1 on n here, which was 1 divided by 5, will just give us the 0.2 on the outside here. So that actually is the solution for question 5 there, and it actually is pretty quick. All you just need to remember is what the n equation is here, which is going to be the sampling frequency divided by the null point frequency to get out what n is. And then you just need to know the standard moving average filter equation, and you just plot in what n is accordingly and state out all the terms as of such. So anyone has any questions on question 5? Alright, I don't think anyone has any questions. Okay, good. So, let's move on to question 6. Question 6 in particular, I'm just going to show you like the general outline on how to do this. So, the triangular window, you basically could get that equation from the lecture notes. What I'm going to be doing here is question 6 part 1, actually for you to figure out how you go about doing the Hamming window. And this is going to be a 9-point Hamming window in particular. So, for the Hamming window, you're going to be repeating the design from question 5. So that means you need to calculate h of n here with an ideal cutoff frequency. And the question you want to be asked is, what is this going to be for our ideal cutoff frequency? Now the question here had where the first null point is at 100 Hz, and a null point is actually could be treated as our cutoff frequency here. So in this case, the ideal cutoff frequency here will be the null point frequency, which is 100 Hz. In designing for h of n here for our Hamming window, and this is also from your lecture notes, h of n will follow the following equation that I'm typed out here, which is going to be h of n is equal to 2 multiplied by fc divided by f sync of, let me incorporate some nice brackets here, 2 pi n fc divided by f. If we substitute in all coefficients here accordingly for fc and f, this is going to be 2 multiplied, and if we put fc and f here, which is going to be 100 divided by 500, and then we say this is going to be sync of what we had in our brackets here. we get h of n here is equal to 0.4 sinc of 0.4 pi of n. We also know that for a Hamming window, and this typically is given to you in a final exam, W of n was equal to 0.54 plus 0.46 cosine of 2 pi n divided by n minus 1. And in this case, because n is going to be 9 points here from the question, that means n needs to go from negative 4 to positive 4. Sorry, so capital N here was 9 points. Common n needs to go from negative 4 to positive 4 to incorporate those 9 points accordingly. So because now you have the range of n, that means you can substitute in n here from negative 4 to positive 4 here for h of n and for w of n here accordingly. And the step that you do here is, after you do that, is that you need to find w of n multiplied by h of n. Alright, so because this is set up here, let's see if I could pull Octave, and if I can get Octave up, I actually could do this for you guys. So let's see, Octave online. Alright, so let's see. So n here is equal from negative 4 to positive 4. So that will set up our range. Let's see how this is looking. This might look a little bit small on your screens. Let's see if I can magnify this accordingly. Right, so that should look better now. Right, then our equation here for h of n was going to be 0.4 sinc of 0.4 pi n. So we can say h, right, so because n goes from negative 4 to positive 4, we can't use that n index here accordingly, because Octave won't allow us to represent this in the negative indexes. So we're just going to say h of n plus 5, because we need to represent this at h of 1 in Octave, is equal to 0.4, much back our equation here, by sinc of 0.4 by pi by n. Okay, so we have a... Alright, so I have to use not square brackets here, I'm supposed to use curly brackets here, normal brackets, sorry. So that will calculate out h here for us accordingly. And then because we have w as well, so this actually will follow w of n plus 5, because we need to accommodate for positive indexes in Octave. It will be 0.54 minus 0.46 multiplied by cosine of 2 pi n divided by capital N here was 9 because it was a 9-point window, so that's 9 minus 1, that's 8 on our denominator. So we have w here accordingly. And then our output, let's call this hw, it's going to be w dot star h. And actually will give us all the coefficients here accordingly for actually what our answer is regarding this. Right, so So that should bring us to the end of question 6 part 1. Yep. Question 6 part 2 and part 3 is basically part 2 you just use the 9-point triangular window. So you get the W of n equation for that. And you start off doing that accordingly. And you just do the same steps as before. Part 3 is just to compare. Questions 7, 8 and 9 are basically just MATLAB analysis for you guys to do. Now, one thing I forgot to explain is that the reason why we start off with this h of n equation here, and this is from your lecture notes, is that you need to start off with the ideal low-pass filter response. And as of such, when you actually did all the complicated math that was done for you, the equation you need to memorize for this is just this h of n equation here for the ideal low-pass filter response. So when you have this, and you plug in your cutoff frequency and your sampling frequency here, which is f, and you get it in h of n, you just need to make sure that when you have the range of n here accordingly, and you have your window function, you're substituting the range of n to get for the h of n coefficients and the w of n coefficients. Once you have those vector values, you just multiply them across accordingly, and you get your final answer here in terms of hw. So what I did is that I set up the range of n here, and then I made sure I calculated for my h. The reason why I did n plus 5 here is because Octave does not allow for negative indexes. So we need to make sure that this index of h here needs to start at h1. We can't even do a h0 index because of how Octave operates. So this is negative 4 here. We need to offset the index here, so that way it goes to h1. But the equation that we had from before here, which is 0.4 sinc 0.4 pi of n, we could just plug that in accordingly here and it will work. So we get our h here, we do the same thing for w, and then we calculate out for h of w. Alright, so in repeating the steps of question 6 here, is that you need to repeat the design of question 5 using a 9-point Hammond window based FIR filter. The first thing is that because we're doing a FIR filter, we need to make sure that we have the ideal low-pass filter response. So the ideal low-pass filter response is given by this equation here, which is h of m is equal to 2 divided by fc divided by fs multiplied by sinc of 2 pi n fc divided by fs. The first thing after we have this equation here is that we need to know what the ideal cutoff frequency is. Now in question 5 here, they talk about how there's a first null point at 100 Hz. A null point at whatever frequency that is could be treated as your cutoff frequency. So we say fc here is equal to 100 Hz. F of s was given to us, which is 500 Hz. So we just substitute that into the h of n equation accordingly, and we get h of n in terms of sinc into this nice form here. Because we're calculating for a Hammond window, the Hammond window equation normally is given to you in any final exam. The Hammond window equation is w of n is equal to 0.54. Hold on, I might have typed in that wrong. Let me make sure I type that in correct. 0.54 plus 0.46, yes, that's correct, plus 0.46, so that means I might have to do a more octave. Right, so you have the Hammond equation here, which is w of n equal to 0.54 plus 0.46 cosine of 2 pi n divided by n minus 1, where this capital N here is the number of points. The number of points here was a 9 point, so this capital N here will be 9. And in order to incorporate these 9 points, and it needs to be symmetrical, common N here needs to go from negative 4 to positive 4. Once we have our h of n equation here, and our w of n equation here, with our common n range, we can then set this up to get the vector values for h of n and w of n accordingly. So let's jump back into Octave here. I'll repeat the steps. N here, so clear all. N here was equal from -4 to +4. This here needs to be a link of 9 values. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9. And it needs to be symmetrical about the 0 point here. H of n is what we need to calculate for next. Now Octave itself does not allow for negative indexes, and it does not allow for a 0 index. So that means we need to make sure that when we have our h of n index here in Octave, this is to start at h of 1. But our equation here can remain the same accordingly, and this n here can have the negative indexes accordingly for n. So we just offset the index here when we're doing this. So h of n plus 5. So I'll just show you what will happen if we did this just with h of n. So 0.4 multiplied by sinc of 0.4 by pi by n. Octave here will complain and say h of -4 subscripts must be either integers 1 to 2 to the power 63 or -1, or logicals, meaning that it only can take positive indexes. So this is why we need to offset the index when we're doing this. So h of n plus 5, because -4 plus 5 will give us a result of 1 here, is equal to 0.4 by sinc of 0.4 by pi by n. And this will calculate out all the values for our h vector. Similarly with w, you need to do the same offset, otherwise it will complain. So this will be 0.54 plus, let me check back this, right, 0.46 multiplied by cosine of 2 by pi by n divided by n minus 1. Capital N here was 9 points, as we can see here from our question. So 9 minus 1 here will give us 8 divided by 8 here. So we'll get our w vector here accordingly. The last thing is to multiply the values of w of n and h of n across each other respect to the vector values. So to do this, let's call our result here h of w. We'll say w dot star h. And this will actually give us our final vector values here. So to give you an idea of how we write out this equation, and I now realize that I forgot to actually write out the equation for you guys. We can say hw of n here, and because we have all the coefficients here, each one of this is going to be represented in terms of the n index that we had from before, from -4 to +4. So it'll be minus 0.00169, because I'm rounding off, of z to the -4, minus 0.0048 of z to the -3, plus 0.0273 z to the -2, minus 0.0633, and this skips to the next page, z to the -1, plus 0.4, because it's symmetrical, it repeats, so this now is going to be z to the 1, this will be z to the 2, this will be z to the 3, this will be z to the 4. And we can see here that the coefficients map, because our first coefficient here, so our first coefficient here maps to this coefficient here even though it's truncated. Our second coefficient here maps to this coefficient here, and so forth as we keep on going. So this one here, this one here, this one is here, this one is here, and so forth as we keep on going. This one is here, this one is here, and this one here is here accordingly. So this would be the, let me make sure I'm saying this correctly, causal form of Z. So someone might have to correct me here. If I'm saying this wrong, is that this may be the causal form here, or this might be the anti-causal form. Basically, there are positive powers of Z here. What we need to do is that we need to make this into the correct form, which I can't remember which term it is right now. But the correct form is basically all of this needs to be in negative powers of Z, because we can't have any positive powers of Z. So this means we need to delete this accordingly by Z to the negative 4 samples. So in doing this, I'm going to copy this. This means this goes to Z to the negative 8. This one will go to Z to the negative 7. This is Z to the negative 6. This will be Z to the negative 5. This here will go Z to the negative 4. This one will be negative 3. This is minus 2. Z to the negative 1. And this one here will just be Z. So need to put this in negative powers of Z only. Causal or anti-causal form. So someone may need to verify which form it is, because I can't remember which form it is right now. But basically the application of it is that you can't have any positive powers of Z here. So you need to transform this into negative powers of Z accordingly. And that will actually give you the final answer for each W of N for that question. Right, so that brings us to the end of all the questions that we can do here accordingly. Are there any vital questions that need to be asked regarding problem set 3 at this point? That's the final question can ask for it to be represented in the anti-causal form or causal form. One of the forms is basically that you cannot have any positive powers of Z. And I'm not sure which form it is, if it's causal or anti-causal. You might have to check back the lecture notes just to verify. But basically, once you have this, and it says that you need to represent it in the particular form, be it that it only can be represented in negative powers of Z. So I'm assuming this might be the anti-causal form. you need to make sure that you delay the equation accordingly so that you only have negative powers of z. So the question will come such that it will ask you to make sure that you represent the final answer in negative powers of z, or it might say, okay, this is the anti-causal form, which may map to the negative powers of z. Any further questions? Yeah, I was waiting for that question in particular. So, questions that might tend to come like your final exam questions would be like questions 1 to 3, question 5, and the first part of question 6. So any one of those questions in particular, so questions 1 to 3, question 5 and question 6 part 1 may come in like a final exam. And I know I promised to put up the final exam papers from more recent years. I actually have to do that today. If I don't do that by today, someone please send my email to remind me so that way I can put them up. So you can actually see like what those kind of questions are that keeps on coming in the final exams in particular. Question 4, which asks for like the conditions of distortionless transmission here. That is just basically a recap question, and it's not really an application question, so it may not come at all. So the questions you want to focus on, repeating this, questions 1 to 3, question 5, and question 6 part 1. If we tell you that you need to design something for a Hamming window, we will give you the Hamming window equation accordingly. The only equation that you need to remind yourself about is this h of n equation for the ideal low pass filter response. You need to actually memorize this equation. We don't give it to you in the exam. Oh yeah, speaking of which, there may be, and I'm not sure about this as yet, an option depending on how this situation is going that your exam might end up going online. And in such a case, when it's online, I think the final exam may end up being open book, but I'm not sure if Dr. Medina is taking this approach as yet. So until I have further information regarding this, it means that I'll have to brief you on the exam accordingly depending on how the exam style is going to be. But I will have an exam tutorial session explaining all of this and what you could do and what you can't do and what to look out for in particular with respect to the exam. Alright, so any further questions at this point? Yeah, typing math is a pain. I don't know if they would allow you guys like to write on paper and then do a snapshot and upload it, or if they might give you like a template or something to type out the math. I don't know as yet. That's it. They're still working on logistics if it makes any sense to do the exam online. Alright, so next class, and I'll pop a forum notice on this, will be next week Tuesday at 10 o'clock, 10 a.m. We'll be focusing on problem set 4 in particular. After we finish on problem set 4, any of the tutorial sessions I'll be doing will be more focusing on the type of questions you may get on final exams. But once I'm holding those sessions, I will put up a forum notice saying the date and time and so forth for those sessions. Yeah, typing the math is kind of a problem in particular. But that's it, they're still working out on how to go about doing this. I mean, if everything is fine by April 20th, we should be resuming as normal, and I mean you'll have your standard written exams like how normal exams are. But if things don't resume as normal, then we have to figure out what the alternatives are. The department can't really give you an update on the exam issue. This is going on at the examination level. So this is actually exam section and at the university principal level as well. So we can't really take a stance on this. We just waiting to see what we can get approved to do and what we can't get approved to do. We need to make suggestions at this point. That's why you're not really getting any updates on the exam issue at this point. The decision needs to be made at a higher level than department. It needs to be made at the university level. Alright, so that should be the end of our stream. I'll put up a forum notice for next week Tuesday at 10 a.m. for our tutorial session. So I'll see you guys then. Alright, later.